In December 2004, astronomer David Tholin received the most terrifying email of his career. A faint dot of light he'd co-discovered 6 months earlier at Kitt Peak Observatory had just been assigned a 2.7% chance of slamming into Earth, the same odds as landing on a single number in roulette. The asteroid was roughly 370 meters wide, taller than the Eiffel Tower turned on its side. The projected energy impact? Approximately 1,200 megatons of TNT. That's roughly 80,000 Hiroshimas detonating in a single flash. Its discoverers named it Apophis, after the Egyptian god of chaos, a designation approved by the International Astronomical Union. And for 2 agonizing days in late December, it held the highest collision threat ever assigned to a tracked asteroid. But the real story of Asteroid Apophis isn't the rock itself. The real danger was a patch of empty space only 600 meters wide, a gravitational keyhole. And until you understand what a keyhole is, you don't actually understand how asteroid threats work, or why April 13, 2029 will be the most watched astronomical event in human history. Here's the principle that explains everything. Orbits are not rails, not fixed tracks carved into space. Every time an asteroid swings close to a massive body, Earth, Jupiter, the Moon, gravity reshapes its trajectory. The closer the flyby, the more dramatic the reshaping. And within the fan of possible exit paths after a close encounter, there exist tiny windows of space, gravitational keyholes, sometimes only a few hundred meters across. If the asteroid drifts through one of these keyholes during a flyby, its orbit gets bent precisely onto a collision course for a future pass, years or decades later. One encounter reshapes the next orbit. One flyby determines the geometry of the next. The entire story of Asteroid Apophis is a story about a single question: will it thread through a keyhole? On June 19, 2004, astronomers Roy Tucker, David Tholin, and Fabrizio Bernardi spotted Apophis from Kitt Peak National Observatory in Arizona. It was catalogued as 2004 MN4, a speck of reflected sunlight drifting against the background stars. They tracked it for 2 nights, then weather closed in, and the asteroid slipped behind the glare of the sun. For 6 months, nobody on Earth knew where it had gone. This matters because predicting an asteroid's future orbit requires observations spread across time. 2 nights of data produce a rough trajectory, like watching someone walk for 2 steps and trying to predict where they'll be next month. The uncertainty is enormous. So when 2004 MN4 vanished, its projected path remained a wide cone of possibilities, most of them harmless, some of them not. In December 2004, astronomer Gordon Garrad at Australia's Siding Spring Observatory independently rediscovered the object. When orbital calculators linked it to the June observations, the geometry sharpened, the cone of possibilities narrowed, and inside that narrower cone, Earth was sitting directly in the crosshairs. Over the following days, each new observation refined the orbit. The impact probability climbed, 1%, then 1.6%. On December 27th, it reached 2.7%. The Torino Scale, the international system for rating asteroid collision threats ranging from 0 to 10, jumped to level 4. No asteroid in recorded history had ever reached 4. Level 4 means a close encounter with a greater than 1% chance of a collision capable of regional devastation. Pause and absorb that. Not a textbook hypothetical, not a movie plot, a real rock tracked by real telescopes with a calculated 1 in 37 chance of devastating a region tens of thousands of square kilometers wide within 25 years. The astronomical community entered quiet crisis mode over the holiday break. And the question dominating every conversation was brutally simple. Are the observations precise enough, or could more data change the picture? Then someone had a brilliant idea. If this asteroid existed in June and December of 2004, maybe it appeared in photographs taken earlier, images captured by automated survey telescopes that scan the sky continuously, archiving everything. This technique is called pre-covery, hunting for an object in data collected before anyone knew to look for it. Within days, researchers located Apophis in archival images from March 2004. 3 additional months of positional data. That doesn't sound revolutionary, but remember the walking analogy. 2 steps of observation versus 5 steps transforms the prediction entirely. Those pre-covery images stretch the observational arc enough to collapse the uncertainty cone dramatically. When the revised orbit was calculated, Earth slid out of the crosshairs. The impact probability for 2029 plummeted to effectively zero. The relief was enormous. But the story was just beginning, because while Apophis would definitively miss Earth in 2029, it would pass terrifyingly close, and during that close encounter, Earth's gravity would reach out, seize the asteroid's orbit, and reshape it, potentially threading it through a keyhole aimed at 2036. So here's a question to test your intuition. On April 13, 2029, Asteroid Apophis will fly past Earth at a distance of roughly 31,000 kilometers from the surface. How close is that really? Consider this. Geostationary satellites, the ones relaying television signals and weather data, orbit at about 35,800 kilometers above the surface. Apophis will pass inside that ring, inside the ring of geostationary satellites, though still beyond the GPS constellation orbiting at roughly 20,000 kilometers. No known asteroid this large has ever been tracked passing this close to Earth. Now, picture what April 13, 2099 actually looks like. Apophis approaches from the Sun's direction, sneaking up on Earth's day side, hidden in the glare. As it swings around, crossing into the night sky, it accelerates under Earth's gravitational pull. For observers across Europe, Africa, and Western Asia, a new point of light will appear, visible to the naked eye, drifting noticeably against the stars. No telescope required. A 370-meter asteroid, bright enough to see unaided, sailing past at roughly 7.4 kilometers per second relative to Earth, about 7.5 times faster than a rifle bullet. But the visual spectacle hides the real physics. During those hours of closest approach, Earth's gravity won't simply bend the asteroid's path around the Sun, it will fundamentally restructure its orbit around the Sun. Before the 2019 encounter, Apophis circles the Sun every 323 days, crossing Earth's orbital path twice per year. After the encounter, models predict the orbital period will stretch to roughly 378 days. The asteroid's entire classification changes from an Aten-class orbit that fits mostly inside Earth's to an Apollo-class orbit that extends beyond it. One flyby, one gravitational handshake, a completely different trajectory through the solar system. This is where the keyhole concept comes alive. During the 2029 flyby, Apophis passes through a corridor roughly 50,000 kilometers wide. Within that corridor, every slightly different closest approach distance produces a slightly different exit trajectory. And scattered within that range of possibilities are gravitational keyholes, each one only hundreds of meters across, each one a precise doorway to a resonant return and potential impact on a specific future date. The keyhole for a 2036 collision was estimated at roughly 600 meters wide. Think about that scale. The orbit of Asteroid Apophis around the Sun stretches roughly 860 million kilometers. The gravitational keyhole that separates a harmless miss from a future catastrophe is 600 meters. That's like threading a needle from across the entire Pacific Ocean, except the needle is tumbling at 30 kilometers per second and the thread is being pulled by every planet in the solar system simultaneously. Between 2004 and 2021, every major radar facility on Earth took turns interrogating Apophis. The Goldstone Deep Space Communications Complex in California's Mojave Desert, the Arecibo Observatory in Puerto Rico before its catastrophic collapse in December 2020. Each radar observation measured the asteroid's distance and velocity with extraordinary precision, down to meters in range and fractions of a millimeter per second in velocity. And these measurements revealed something crucial beyond position. A faint, persistent force slowly nudging the asteroid's trajectory over time, the Yarkovsky effect. The Yarkovsky effect works like this. Sunlight heats one face of a rotating asteroid. As that heated face rotates away from the Sun, it radiates the absorbed energy as infrared light. That thermal emission carries a tiny amount of momentum, a whisper of thrust. For Apophis, this ghostly force shifts the asteroid's position by roughly 170 meters per year. Barely anything, but over decades, those meters compound. And when the question is whether a rock threads a 600-meter keyhole, 170 meters of annual drift becomes potentially the difference between a near miss and a civilization-altering impact. In March 2021, radar observations from Goldstone pinned down the orbit of asteroid Apophis so precisely, incorporating the Yarkovsky drift with measured certainty, that NASA officially ruled out any Earth impact for at least 100 years. Every keyhole was mapped. Apophis will miss every single one. If you followed that entire chain, discovery, precovery, orbital refinement, keyhole identification, Yarkovsky correction, and final clearance, you now understand the complete methodology of planetary threat assessment better than most people ever will. That sequence is exactly how every potentially dangerous asteroid gets evaluated. Apophis simply happened to be the first one that tested the system under genuine stakes. Now for a prediction that reveals something deeper. In September 2022, NASA deliberately crashed a spacecraft called DART into a small asteroid moon named Dimorphos, orbiting a larger asteroid called Didymos. The goal: test whether a kinetic impact could measurably change an asteroid's orbit. Dimorphos orbited Didymos every 11 hours and 55 minutes. The DART spacecraft weighed about 570 kilograms, roughly the mass of a grand piano. Dimorphos weighed approximately 4.3 billion kilograms. So what do you think happened to the orbital period? A few seconds of change? A few minutes? 33 minutes. The orbital period dropped from 11 hours 55 minutes to 11 hours 22 minutes, a roughly 4.5% change from a collision that, in mass terms, was like throwing a golf ball at the Great Pyramid of Giza. And the reason is beautiful. DART didn't just push Dimorphos. The impact excavated an enormous plume of debris. Thousands of tons of rock and dust that sprayed off the surface like exhaust from a rocket engine. That ejector carried momentum away from the asteroid. Newton's third law did the rest. The debris contributed more to the deflection than the spacecraft itself. That was the first time in the history of any known civilization that a species intentionally altered the orbit of a celestial body. Let that settle for a moment. But the DART mission, spectacular as it was, illuminates a terrifying constraint. The deflection worked because there were years of preparation, a known target, and time to design, build, and launch a spacecraft. The actual velocity change was tiny in absolute terms. To push an Apophis-sized asteroid away from a gravitational keyhole, the intervention would need to happen years, or preferably decades, before the critical flyby. The earlier the push, the smaller the required nudge, because small velocity changes compound over orbital time, the same keyhole physics that creates danger working in reverse. Wait too long, and no technology currently on Earth generates enough force. This is precisely why the 2029 Apophis flyby matters, despite the asteroid being confirmed safe. NASA's OSIRIS-APEX mission, the spacecraft formerly known as OSIRIS-REx, which collected samples from asteroid Bennu and returned them to Earth in September 2023, has been redirected to rendezvous with Apophis immediately after the 2029 encounter. It will orbit the asteroid for 18 months, mapping its surface and studying how Earth's gravitational tidal forces reshaped the rock during closest approach. At 31,000 kilometers, the gravitational gradient across the asteroid's 370-meter body will be strong enough to potentially trigger landslides, reshape surface features, and alter its rotation rate. Apophis isn't solid steel. Radar observations suggest it's likely a rubble pile, a loosely bound collection of boulders, gravel, and dust held together by its own feeble gravity. Earth's tidal forces may literally rearrange its surface geology in real time, and OSIRIS-APEX will be there to document it. If you could somehow stand on the surface of Apophis during closest approach, which is impossible since the surface gravity is roughly 100,000 times weaker than Earth's, meaning a casual jump would launch you into orbit, you would see Earth spanning roughly 20 degrees of arc, about 40 times the width of the full moon, dominating your entire view. Not a distant blue marble, a wall of ocean and cloud and continent close enough to resolve city lights on the night side with your bare eyes. And beneath your feet, the ground would be shifting, settling, perhaps fracturing, as Earth's gravity reached across 31,000 kilometers of vacuum and physically rearranged the rock beneath you. The loudest sound on Earth that day would be silence. The most dramatic event in the solar system would be invisible to everyone except the instruments pointed at a tumbling speck of light. But here's what should genuinely unsettle you about the asteroid Apophis story, and about near-Earth asteroids in general. On February 15, 2013, a rock roughly 20 meters across, approximately 18 times smaller than Apophis, slammed into Earth's atmosphere above Chelyabinsk, Russia, at 19 kilometers per second. Nobody saw it coming. Zero warning. It approached from the direction of the Sun, the one region of sky that ground-based telescopes cannot observe. The airburst released roughly 500 kilotons of energy, about 30 times the Hiroshima bomb. The shockwave arrived as a wall of pressure that shattered windows across 6 cities. Over 1,500 people were injured, mostly by flying glass. 20 meters, invisible until atmospheric entry. Now, scale that up. There are an estimated 25,000 near-Earth asteroids larger than 140 meters, the threshold for devastating a major city. As of recent surveys, roughly 40% have been catalogued. That leaves approximately 15,000 asteroids large enough to end a metropolitan area, each one orbiting the Sun right now, drifting through gravitational keyholes that have never been mapped because nobody knows these objects exist yet. So here's the final prediction question. If an Apophis-sized asteroid were discovered today on a confirmed collision course with Earth and impact was 10 years away, how much would its velocity need to change to miss entirely? Kilometers per second? Meters per second? The answer, roughly 1 centimeter per second, slower than a walking snail. Applied a decade early, that single centimeter per second compounds into an Earth diameter miss distance at arrival. That number, 1 centimeter per second, is arguably the most important number in planetary defense, and almost nobody outside the field appreciates it. The exact same keyhole physics that makes asteroids dangerous is precisely what makes them deflectable. Small perturbations compound over time. That works in both directions. The gravitational keyhole is both the threat and the solution, depending entirely on whether the asteroid was found early enough to act. Return to where this started. December 2004, David Tholen staring at an email with a 2.7% impact probability. Roy Tucker and Fabrizio Bernardi's faint dot at Kitt Peak, nearly lost to weather. Gordon Garrett's rediscovery from the opposite hemisphere. Archival photographs nobody thought to search until the stakes turned existential. A Christmas scare that stress-tested humanity's entire asteroid detection infrastructure and found it working, barely, just in time. On April 13, 2029, roughly 2 billion people will look up with nothing but their eyes and watch Asteroid Apophis cross the sky, a point of light drifting among the stars, closer than the communications satellites, closer than anything that size has ever been tracked approaching this planet. And it will miss, not by luck, by mathematics, by the accumulated labor of astronomers who found a faint dot, lost it, found it again, dug through old photographs, measured its thermal radiation, mapped its gravitational keyholes, and determined to within meters exactly where a tumbling mountain of rock would be a quarter century in the future. That is not just science, that is arguably the most extraordinary predictive achievement any species has ever accomplished. And yet, somewhere out there right now, roughly 15,000 similar rocks continue their silent orbits, threading through unmapped keyholes, untracked and unnamed. The next Apophis is already there. The only question is whether someone spots the faint dot in time. Like if this was interesting, hit the subscribe for more and turn that notification bell on.